Hello, everyone. Welcome to the webinar. We're just going to give people a minute or so to join before we get started. Hi, everyone. I think we should get started. Thank you for taking the time to be with us today. I'm Malcolm Pantaki, co-founder of the Revolution in Simulation online community and VP of Analysis Solutions at Aris Corp. We are joined today by Barna Zabo and Ricardo Actis of ESRD, and they'll be presenting an important topic: why rigorous simulation governance practices are essential if you wish to deploy the full power of simulation automation for predictive maintenance of expensive assets in the field. The RevSim initiative was launched at the NAFEM's CASE conference in 2018. It's a free web portal that gathers together in one online space all the resources that you might need to take your simulation investments to the next level. It focuses on next generation simulation usage, helping your organization to maximize the impact of simulation on your business goals. Case studies are a pretty important resource that's available on the portal. We've gathered together over 100 interesting cases, and the list is growing. You can find out what your industry peers are doing to increase the impact of simulation in their organizations. So please join the community and contribute your own success stories to be shared. A number of industry leaders have volunteered their expertise, knowledge, and time to be moderators of a growing list of topics of interest. In fact, the speakers today at today's webinar are also moderators on RevSim. They curate freely available materials and reference them on the different topic pages, which you can access under the How It Works menu. You can ask questions, start discussions with the moderators, so please do contribute your thoughts and materials to share with the community. With the help of the moderators and our community, we've gathered together a very large set of resources, and you can access these under the Resources tab. Very few of these are actually stored on the site. The site provides a short summary of a resource and then points to its original location on the web. Finally, RevSim has a growing list of sponsors. These are industry thought leaders that are an integral part of this revolution in simulation. The sponsors provide more than just financial resources to the community and are critical to the ongoing success of this initiative. If you're a solution provider at the cutting edge of simulation, please join us at revsim.org and contribute. Now, this is the 6th webinar in the new Learn from Your Peers webinar series hosted by RevSim. The next one is scheduled for late June. SAIC and Phoenix Integration will be presenting on the exciting topic of MBSE and simulation. Links for today's presentation and the recording we sent to you soon. Recordings of all the prior webinars are also available on the site. Now, if you have any questions, please type them into the questions panel so that we can respond to them. With this, I will hand it over to Barna and Ricardo at ESRD.
Don't forget to unmute.
Great, we can see your screen.
Right, thank you, Malcolm. Good morning, everyone. My name is Ricardo Actis. I'm here with Dr. Barna Sabo. We are both from ESRD. ESRD is an independent software vendor with headquarters in St. Louis, Missouri. And our main focus is on research and development in computational solid mechanics and the application of finite element analysis-based numerical simulation tools to accelerate standardization and automation of processes for the aerospace and defense industry. This presentation, which is based on R&D work sponsored by the US Department of Defense, addresses the role of simulation governance in condition-based maintenance, with particular reference to a mathematical model formulated for the prediction of fatigue life of structural components in the high cycle regime. We're having a little difficulty allowing this to, yeah. Okay, sorry about that. Now it's working. So what is the goal of the presentation? Is to review the process for the formulation and validation of a mathematical model for the prediction of fatigue life of notched mechanical components, as I mentioned earlier, in the high cycle regime, in support of condition-based maintenance decisions through the application of the concept and procedures of predictive computational science. That is verification, validation, and uncertainty quantification, VVOQ for short. A simplified workflow of the process is discussed next. Considering a high-value asset such as a rotor assembly of a helicopter, let's suppose that the flaw is found in one of the critical components, as shown in the picture. To assess the effect of the flaw in the remaining fatigue life of the component, a predictor is computed by solving a local model with the flaw loaded with the reference stress that is available from the pristine condition of the flaw specimen. The predictor, as we will discuss in more detail later, is constructed as an integral average of a function of stress over a solution-dependent volume, which is defined by a calibration parameter beta. Therefore, the picture on the left, top left, shows that relationship, the calibration parameter, which is a function of the highly stressed volume of material around the flaw. And we will define a little more later what that means. Once the integral average is available, a sigma equivalent stress is computed. In this case, we are using a expression, Smith-Wasson-Tupper, and we will discuss about that a little later too. These values then enter into the statistical model to determine the number of cycles to failure. With this approach, it's possible to meet the condition-based maintenance need to move flow damage components removals from unscheduled to scheduled maintenance action.
So we will be discussing, excuse me. Yes. We will discuss the formulation of a mathematical model designed to support condition-based maintenance, as Ricardo explained, relating to the high cycle fatigue environment. This model is representative of mathematical models used in the applied sciences in general. The methodology we will demonstrate here fits into a framework called the Methodology of Scientific Research Programs, or MSRP for short. This was proposed by Lakatos, a science philosopher, in the 1960s. There is one essential modification to Lakatos's ideas is necessary, however, and you will hear about this over and over again today. Lakatos did not define the domain of calibration, which is an essential attribute of any mathematical model. He was interested in how scientific progress occurs in general. His field of inquiry included not just the hard sciences, but also the social sciences. And that is why he wasn't focused on that important attribute. We are focusing on a much more narrow application of modeling to those used in applied sciences. And why is this essential? Why do I emphasize the domain of calibration as being an essential part of any mathematical model? It is because if we allow the domain of calibration to be small enough, then any model, even pseudoscientific models, can be validated. So therefore, we have to be very careful of what do we mean by a model and what do we mean by validation, and that can only be assessed if we understand what the domain of calibration is. Note that in our presentation, the mathematical models are understood to be independent of the method used to obtain a numerical solution. I emphasize this because numerical simulation is often confused with finite element modeling. The difference between the two is like the difference between astronomy and astrology, or chemistry and alchemy, or science and pseudoscience. In applying the methodology of scientific research programs in a particular model development project in industrial settings requires the exercise of simulation governance. That is the exercise of command and control over all aspects of numerical simulation, which is typically a multidisciplinary undertaking. We shall see that model development projects are open-ended. No one has the right to claim the last word. The management of data and revision of mathematical models in the light of new ideas and information requires careful management in industrial and research organizations. So let me say a few words about what revolution in simulation means and how I understand it. What has changed in numerical simulation that deserves to be called revolutionary change? In my view, it is the recognition of the central role of mathematical models in both the foundational and applied sciences. The name for this is model-dependent realism. This term was coined by Stephen Hawking, the well-known theoretical physicist. The essential point is that we perceive reality through models. This is true in the foundational sciences, the applied sciences, and even in everyday life. The consequence of this is that the notion of physics-based model has no meaning. The notion is empty. It is the other way around. We should think about model-based physics. Another term that causes a great deal of confusion and therefore hinders progress is finite element modeling. This is a fuzzy term that mixes the idea of model with the method used for finding an approximate solution. A mathematical model is a precisely stated idea of some aspect of reality. It has a strong intuitive and creative component that demands logical consistency, and that's what the mathematical part supplies to this enterprise. It has an exact solution that exists completely independently from how an approximate solution is obtained. The process by which the finite element solution is obtained is entirely science-based. It does not have much room for creativity. The creative aspects of the obtaining finite element solution are confined to designing a discretization strategy. What I understand revolution in simulation to mean is placing numerical solution on a solid scientific foundation. The field is called predictive computational science. So let me go now to what is a mathematical model. We view and we teach that a mathematical model is nothing more, nothing less than a transformation of one set of data into another. We will consider this particular model. And before I go into that, let me just say and refer back to the methodology of scientific research projects as outlined by Lakatos for the first time. In his view, a scientific research project has a set of assumptions, some of which are classified as hardcore assumptions, and the others are called auxiliary hypotheses. Here, we are talking about a mathematical model which is designed that you have the conditions that Dr. Actis described, finding a flaw, finding the conditions around the flaw in the stress field, and then making a prediction of the probability of failure. So this is the output, the probability of failure. In between, there is this process of transformation. And the transformation is based on a mathematical model. And the mathematical model we use the linear elasticity because it's in a high cycle range. So therefore, it is reasonable to assume that the stresses are not too large and the linear elasticity can be applied with some modification, however. This is the hardcore assumption. Then we have to construct a predictor, and Dr. Actis alluded to that it will be an integral average of the stress field in the neighborhood of the stress riser. And so therefore will be some additional discussion on that point. And then since the phenomenon itself is a statistical one, in other words, a random process, because the material happens to fail in a random way. If you have same specimen tested 15 times, you will get 15 different outcomes. But however, they organize themselves into a statistical distribution that is representative of a material property. And we will be addressing that. So these two are the auxiliary hypotheses. So in Lakatos's view, if in the hardcore assumption something fails, then the entire project goes out the window and you cannot proceed anymore. However, the auxiliary hypothesis can be adjusted based on observations and based on various ideas. And this is where the art and science of model construction meet. So now I turn it over to Ricardo, so he will share with you some words of wisdom.
Thank you. Well, what is the role of the predictor is simply generalization of the SN data to triaxial stress distributions. In the mathematical model, it is assumed that the propensity of a metallic material to fail in fatigue is characterized by fatigue data collected from notch-free coupons under constant cyclic loading at various mean stress level. This is called the SN data. The test data used for this work was collected from NACA report from the 1950s on 2024 T3 aluminum specimens that were cut from 0.09-inch thick plates. The SN data are then transformed to an equivalent stress versus number of cycle to failure relationship, which is used for calibrating the statistical model. The statistical model provides the probability density function for a fixed equivalent stress level from which probabilities of fatigue life can be calculated. The typical notation used in presenting this type of data is shown on the right, where sigma A is the alternating stress, sigma M is the mean stress, R, which is the ratio between sigma minimum and sigma maximum, the loading cycle, is called the load cycle ratio, and sigma equivalent, SEQ is the equivalent stress defined there, which establishes the relationship between a constant amplitude cycle of arbitrary mean stress and the constant amplitude cycle with zero mean stress, also known as the full reverse cycle. That allowed the consolidation of all data with different mean stresses represented in a single diagram. The next point in our, what Dr. Savo described in the components of the mathematical models, is the predictor. The predictor was formulated on the assumption that the onset of fatigue failure can be correlated with the integral average as a function of stress of a solution-dependent volume. The integrand, as shown in the first equation, is a linear combination of two stress invariants, I1, which is the sum of the normal stresses, and sigma bar, which is the von Mises stress. The solution-dependent domain of integration is defined by the expression of omega c, where x is the position vector, sigma 1 is the first principal stress, and sigma max is the maximum value of the principal stress at the notch root. This is schematically indicated here on the top right, when there is a notch and the area where the maximum stress occurs at the root of that notch. The material-dependent parameter beta is determined by calibration and is a function of alpha and the highly stressed volume of material around the notch. That dependence with the stress volume is characterized by the parameter gamma. So omega gamma, which is the highly stressed volume, is those points around the flow where sigma max is greater than gamma, sigma 1 is greater than gamma plus sigma max. An indication of the highly stressed volume is in red on the lower figure on the right side. The highly stressed volume is the one that allows us to write the relationship between beta and to obtain the parameter beta for different type of notches. In the statistical model, we use a 5-parameter statistical model, and based on investigation that we reported in previous work, indicated that the random fatigue model proposed by Pascual and Meeker in 1999 is well suited for the statistical representation of the SN data of aluminum alloys. The statistical model is based on the assumption that the random variable log 10 of the number of cycles to failure, as indicated in the first equation, is normally distributed with mean mu and a standard deviation S, which in this model was assumed to be constant. Therefore, the expression for the mu is given in this expression as a function of A1, A2, G of alpha, which is the driver that was defined, the predictor that was defined in the previous slide, and V, which is the fatigue, is related to the fatigue limit. B has to be greater than 0 unless that log 10 of G alpha. This particular expression of the in the random fatigue limit model, V is a random variable, which is normally distributed as well with mean mu f and a standard deviation SF. And for the particular material that we are referring to in this presentation. By the way, the notation here, 24ST3, was the older notation that existed in the 1950 to represent the 2024 Ts. The values of the fatigue or the model parameters, A1, A2, S, mu F, and SF are shown, and they were obtained using maximizing the likelihood function. So the important thing to recognize is that while the data tell us what did happen during the test, the statistical model tell us what may happen after we try to predict failure. The calibration statistical model, put it in context of the segment that Dr. Savo showed about the mathematical model. We are now addressing this point statistical model, the 5 parameters. These are the 5 parameter statistical models that have been calibrated. The data points obtained by the experimentation are shown as open squares. The open triangle means runouts. That means that the test was stopped at a given number of cycles. And the range, in this case, of validity of this statistical model is the range in which we have values, experimental values. And that range in this case is between 10 to the 4th and 10 to the 7th. Since our goal is to predict the prediction of high cycle fatigue, that means that we are using a statistical model, we can work reasonably well within that range. In order to calibrate the predictor, we had to use data that of notch specimens. In this same NACA data package, there was information about many different notch cases. This is one example of them. And the calibration, as we saw, has 3 parameters. The outcome of that calibration effort was using 296 notch specimen of 2020-43 is showing this page here. You can see that all the data points after the calibration was performed, most of them in a band that is contained between the 5% and the 95% quantity. And another example of the type of a specimen are shown in the left and the right of the graph. So once we have the statistical model, we have to understand what are the limits on the domain of calibration. So the domain of calibration in this particular case is limited by the assumption of small strain linear theory elasticity, which can be relaxed by the item 4 shown below, namely assuming that a small scale plasticity is allowed and then putting a value on what that limit should be. And that will be illustrated later in the validation phase. The other limiting calibration is by the range of cycles in which the SN data are available, and we show that in this particular case is between 10 to the 4th and 10 to the 7th cycles. And also the interval of the highly stressed volume on which data was calibrated. So the highly stressed volume, there is in 2 dimensions, just to show it for simplicity. There is a state of stress. The highly stressed volume is defined as that volume of material for which the first principal stress is greater than 85% of the maximum stress. And then we can put a limit on the integration volume, which is V sub C, which is the volume that depends on alpha, beta, and gamma, which is the integration volume, and then the V sub Y LD, which is the yield volume, which is the area that the stress sigma equivalent stress is greater than the yield strength of the material. And then we can put a limit on that, and then what we do is reduce the range of the calibration of the predictor.
Okay, so I continue it from here. So Ricardo walked you through the process of calibration, and as we have seen, that there are 2 parts. One of them is the 3-parameter predictor. That's one of the auxiliary hypotheses that we formulated. and the other one is the 5-parameter statistical model. Together, eight parameters have to be adjusted in order to fit the available data. And this is essential in the calibration of models. On the right-hand side, you see the universal categories. One of them is the formulation, then the calibration that Ricardo just walked you through, and then the third one is the prediction. Now, what does it mean, prediction? Now that we have calibrated the predictor and the statistical model, we are given a set of test conditions under which our predictive performance of the model is going to be tested. So this is the whole idea of preparing a project, achieving to test the predictive performance of the model in validation. So in order to validate something, you have to make a prediction based on your calibrated model. And so the project that we found was a work that was much later. Ricardo referred to the calibration as being rooted back in the NACA days, before even NASA was existed in 1950s. And the data that we found in the literature was in 2016. So about 60 years elapsed between the time that the calibration was done and the data that we used for validation was obtained. And this involved the specimen that you see in this slide, which were machined from drawn tubing, whereas the calibration was based on commercial sheets. And it was tested only in under uniaxial conditions. Here, the test was performed under both axial, torsional, and combined loading. And we are particularly interested in the combined loading because until now, that has not been tested. So we constructed the model, we calibrated it, but now there is a new loading condition that we will be considering, for which the model is completely outside of the domain of calibration. And this is the whole idea of testing a model, not within the domain of calibration, where it acts as an interpolator, but outside, where it is essentially based on extrapolation, and see if it can be extended to a larger domain of calibration. And that's what we will be discussing. Now you see this hole was the inside diameter is 25.4 of the tube was 25.4 millimeter, and the hole was just a small hole drilled into it as is shown. Okay. So what does the prediction look like? Well, I'm just focusing because I don't want to walk you through the entire process, but we are really interested in the combined torsion and axial loading case, which is outside of the domain of calibration. And here, the predictor is obtained for 31.6 KSI, and that you see on this slide. And what is this survival curve? The survival curve is based on our statistical model, which is saying that given a predictor, in this case it is fixed to 31.6 KSI, we are asking what is going to be the probability that it will survive to a certain number of cycles. So we kind of arbitrarily fix the 5% and the 95% probabilities as being the limits for which we are making a prediction. And these limits happen to be 77,000 and 671,000 cycles. And we say that we are predicting that when this test article is subjected to the test conditions that I just mentioned, then somewhere the outcome will fall in between those two limits. And so now we have reached the validation test. This is what we performed the prediction. And in order to do the validation, we need, of course, fresh validation data. In this case, this was revealed to us, what the validation data was ahead of time, but ideally, because it was in the published literature, but ideally, the team that does the model construction and making the prediction should be completely blind to what the outcomes will be. This is in order to prevent a human failure of post-dicting something instead of predicting. So therefore, we believe that in a proper protocol, the prediction has to be produced before the validation data becomes available, okay? So the combined in-phase loading, there were 2 specimens tested under ideal conditions, namely 31.6 KSI G alpha. Our predictor value is a number which is given here. And the outcomes were 130 and 302 KSI. So it fell, as you see, very nicely between the predicted range. So we were very happy because this means that the model that was calibrated under much more restrictive conditions is actually functioning reasonably well outside of those restrictive conditions, and therefore the domain of calibration can be extended to combined loading. So now if you look at the all results of the calibration, you will see that there are 13 specimens were tested, some in axial, some in torsional, some in combined loading. And you will see the number of cycles in the column, but please fix your attention to the predicted probability of survival. That is in the 4th column in this table before you. And that comes from the survival curve that we generated. So therefore, we know what the probability of survivals are. The result fail and pass means did we fail or pass the predicted interval? And let me just say to specimen number 11, which is a runout, this is unpredictable, so therefore we take it out of consideration. We will therefore not consider in a validation study all 13 specimens, only the 12 specimens that actually failed. Out of this 12 specimens, 3 of them didn't fall into the predicted interval. The number 1, number 2, and number 7 failed outside of the predicted interval. So therefore, we predicted 9 successes in 10 trials, but we had 9 successes in 12 trials. So the question is, how should we understand this result? Before moving to the next slide, I'd like to remind you of this ratio between the size of the inelastic zone, the yield zone, and the volume of integration that we use for calculating the G alpha. This is a limit, once again, coming back to the domain of calibration. It is necessary to prescribe limits on what parameters the calibration is meant to be valid. And so therefore, this is an essential parameter, and you will see in the remark stage that 2 of those that failed the test fell outside, and this parameter was greater than 10%. Okay? So let's analyze the validation data. We said that we predicted 9 out of 10 specimens to be successful in a validation test. Instead, we had 9 out of 12. So let's see, what does it mean, 9 out of 12 and 9 out of 10? Well, this one is a very fundamental statistical result, and that is that the probability of n successes in M trial is given by the binomial distribution. The binomial distribution is the formula in front of you, where theta is the ratio of the successes to the total number of trials. In this case, it would be 0.9 because we predicted 9 out of 10. In validation, however, we're interested in the inverse problem. We would really like to know what is the probability that the theta is going to be a certain value, and that is given by the Bayes theorem. So if you are familiar with the Bayes theorem, then this is a very fundamental point. If not, then there's no point in going any deeper in that, because it's too large of a topic for us to address completely here. So let me just say that there's a theorem in statistics called Bayes theorem that allows you to estimate the probability of occurrence of a certain parameter. Let's turn to the next slide. And we are using here inferential statistics. We have certain information about the probability of the distribution prior to coming into possession of the outcome of validation experiments. Here we assume that we are completely ignorant about what the distribution of theta is, and therefore assume uniform distribution. I'd like to mention this to you that in practice, however, as you're updating a model or you're testing another model against the data, any prior information that you can have can be factored into this Bayesian formula that you saw in the previous slide. So then we're interested in the value of theta that maximizes the probability of theta given the available data. And the smallest of 9 confidence interval or credible interval. And in classical statistics, you talk about confidence intervals. In Bayesian statistics, it is called credible interval. And the reason it's a difference between the two is because in the Bayesian statistics, you can take into account prior information that you have about the distribution of theta. Okay, so here is the distribution of the probability of the distribution of theta. And as you see in the, we predicted 12 out of 12 tests, we predicted we obtained 9 successes. And so the distribution of theta according to this is represented by this curve. The theta null is the theta 0 is the outcome of the ratio of 9 divided by 12. And that is the experimental outcome. That's the most probable value given the data that you received. And the predicted one of 9 out of 10 is seen on the right-hand side on the curve. So therefore, the credible interval is the interval under the shaded curve, shaded part of the curve. That's 95% credible interval is given by the limits of theta 1 and theta 2. So therefore, we are very precise in making predictions in a statistical sense. Okay, so what would be different if we would have had a perfect score? If we had a perfect score of 9 out of 10, then we still would have a credible interval, which is not small. And this is, you cannot avoid having that, because there's always a possibility that there is a chance that you will observe so many, even though the model is completely wrong. So therefore, that is factored into this picture of saying how certain can you be. So you might ask, well, what would it take to reduce the credible interval to much smaller so that we could be more sure what the predictive parameter theta is? Well, the problem here is that the credible interval is related to the square root of the number of experiments you have available. So therefore, if you want to have the credible interval, you have to quadruple the number of test results. And usually in the fatigue community, we are data poor, and we really don't have the luxury of having a whole lot of data available to us. So therefore, that is really not a feasible thing in practice, okay? So therefore, we come to the, we come to the update of the calibration. So we have passed the validation test. That means that we actually do get exactly what was predicted if we limit the size of the inelastic zone to be not more than 10%. Then we get 9 out of 10, and that's exactly what we have predicted. So therefore, we passed the validation test. What does it mean? Well, you saw that we used the calibration data before, and we set the parameters of the model to calibrate against that set of data. But now, because of validation, we have a new set of data. So therefore, we are obligated to merge this data with the previous calibration test and recalibrate the model because we now have more information. And this is the whole idea that needs to be managed under the simulation governance policies that is an organization has to apply for each model development project. And so therefore you need to create and update the documentation as well. And so this is a very important part of maintaining the records, of maintaining a track and trail of the model development process, and therefore going through this and keeping records and documentation so that the corporation can have a continuous updating in an open-ended process. Okay. So the entire model development process is now before you. We stepped you through every piece. And on the right-hand side, I'd like to point out to you once again, we have the formulation, calibration, prediction, validation, and disposition. Now, these are universal categories, whereas we talked about a particular model development project with a particular goal and aim, which is typical of model development in the applied sciences. They belong in the generic categories or the universal categories that are indicated on the right. And you cannot escape those. You have to follow these steps, no matter what your objective or goals are, those universal categories will hold, okay? Now then the question is it possible, you might ask, is it possible that I have two different models calibrated by different individuals and with different results, and they make the same prediction? How do I know which one is better? Well, this is the problem of ranking. A model is generally not rejected because the outcomes fall outside of the 95% confidence interval or credible interval. This is a most unusual case. The model is rejected only if you find a better model than that. So therefore, the idea of what is a better model is defined once again, comes back to the Bayesian statistics. And this is called the posterior ratio, called K, that is indicated here. This is the ratio of the probability of model 1, given the data that you have available to you, the probability of model 2, and what is this ratio? And this can be calculated usually by the way it's done is usually it's assumed that the probability of model 1 and model 2 is about the same, and therefore it is simply the ratio of the likelihoods which are easily calculated given the statistical model. So therefore, if this ratio comes out to be between 3 and 1/3, then the two models will be in a tie, in a virtual tie, because model development is an open-ended process. So data verification is essential, and this is emphasized through the simulation governance. Okay, I'll let Ricardo close it because you must be tired of hearing it.
Well, you still have one more to go.
Okay.
So what we have seen is that the foundational elements of predictive computational science and verification, validation, and uncertainty quantification. And by verification, in our case, we refer to the solution verification primarily, which is whatever mathematical model we use And we have to obtain a solution, like in the case of our predictor, which is an integral of a function of stress over a volume. And that solution is obtained by the Feynman method. There is an approximation associated with that computation. So we had to use the verification procedure to do that. Does not make sense to try to validate a model which cannot be verified first, that the numerical solution is close to the exact solution of the problem. And we also saw how uncertainty quantification plays a role, because the data that we have defines the dispersion of the prediction. We would like to have a very narrow band so that when we go between 95 and 90%, the interval of the prediction is very tight, but that depends on the quality of the data. And then we have to live with the data we have, and therefore the statistical model is fundamental. Without it, we cannot make the predictions. One important thing that we emphasized earlier and repeat here is that the formulation of mathematical models is independent on how the numerical problems are solved. And therefore, the mathematical model has to be formulated in such a way that the exact solution exists. The domain of calibration is also essential, an essential attribute of the mathematical model, because it means that, as was demonstrated with the mathematical model in this discussion, we had to restrict the applicability of the mathematical model based on the ratio between the plastic volume and the integration volume. And another important consequence of this procedure is that the mathematical models is always a validated model within the domain of calibration. That means that on a sufficiently small domain of calibration, almost any model can be validated. So we have to be careful, because if somebody has a validated model without telling what the range of calibration was, it's possible to use that model in the wrong interval. The outlook is that the prerequisite for a systematic application of the concept of computational science exist and are sufficiently mature for industrial application. This has a multidisciplinary aspect. From the engineering point of view, the formulation and interpretation contain both subjective and objective elements. The applied mathematics, the verified estimation of the quantity of interest is an objective measure, can be objectively determined, and the statistics provide for the data analysis, which again contains subjective elements and objective criteria. When we describe the use of the fatigue random limit model, that was a decision based on some subjective elements, and it has to do with the amount of data that you have, the type of data, what material is involved, and once that is selected, there is an objective criteria. Once you set up the model, then you get the parameter, get the ranges, and you have to use that information for the validation process.
Okay.
Oh, this is also mine, yes.
It's yours.
Well, continue with the outlook. There are substantial economic benefits of applying the procedures of simulation governance. That includes proper allocation of resources between simulation and experimentation, accelerated certification of design rules for new materials, and improved condition-based maintenance decisions. And for all that, simulation governance is essential. One of the interesting comments once I heard is that everybody believes in the experimental results except for the guy who did the experiment, and nobody believes in the prediction results except for the person who did the calculations. And that perception that has persisted for many years can be rooted to the lack of following the simulation governance procedures, because under simulation governance procedures, under the framework of simulation governance, then both the experiment has to be understood from the statistical model, and the simulation has to be understood from the predictive computational science, separating the model definition from the model solution.
All right, so this is the last slide. I just wanted to say a couple of words to where I see obstacle to progress in putting the simulation enterprise on a solid foundation. One of them is, my impression is, and may be wrong, in some particular cases, there may be exception to this, but generally speaking, management does not fully appreciate the magnitude of unrealized economic potential in numerical simulation. In other words, because they do not exercise, as a rule, simulation governance, they're not getting what they could be getting out of numerical simulation if the process was properly managed. And as we have seen in this presentation, there's an underlying conceptual and practical basis for doing that. And we saw an example in this project description relating to the predictive maintenance. The other problem is somehow over the years, the groupthink developed in the community of people working in numerical simulation, and this is not healthy. For example, there are fuzzy notions, like I mentioned, finite element modeling, where the subjective aspects of model definition with the objective process of finding a verified numerical solution to a mathematical problem is confused with the way that the numerical solution is obtained. Then the notion of physics-based model is also empty. And here, let me quote in closing Stephen Hawking's statement, which I completely agree with. I take the positivist viewpoint that a physical theory is just a mathematical model and that it is meaningless to ask whether it corresponds to reality. All that one can ask is that its prediction should be in agreement with observation. And that concludes our presentation.
Thank you, everyone. And if there are any questions, we'll be more than happy to answer them.
Everybody's completely intimidated.
Maybe. Well, Malcolm, if there are no questions, I think that we can end the presentation.
Okay. Again, if anyone has any questions, just raise your hand or enter it in the question box. If you prefer to speak, maybe I could just unmute everybody as well.
I forgot to put the last slide here, sorry, to indicate that they can use the Q&A window.
All right. I think we have no questions right now. The recording will be made available to everyone and will be on the RevSim site. So thank you all for your attention. Hope you have a wonderful day. Bye for now.
Bye. Thank you all.